Hello and welcome! In today's video, we're just going over another method for finding volumes. So one of those big things in calculus is finding volumes. There's a reason why we have several methods to do it. Whether it be 3D calculus or rotations around some axes. So what we're going to be doing today is really investigating another way to really evaluate these volumes, and more specifically, volumes for functions where we don't specifically have a way to get them in terms of y, or practically get them into terms of x's, and more specifically, just generalize the entire process. So to start out here, let's say I have a curve y is equal to x squared minus x cubed, and I want to rotate this curve about the x, or about the y axis. Well, when I do this rotation, what you might notice is that I'm going to have a radius here. Let's call this radius r. But I'm also going to have another radius here, a much larger radius. We could do maybe a disk method, maybe something else, or a washer method, but that would be very complicated, and we need a simpler way of doing it. So let's introduce a new idea. What if, instead of dividing up into small little cylinders, or sorry, not really cylinders, well, yeah, I suppose they are cylinders. We're going to, or the way that we're going to evaluate this is we're going to take a cylinder with a chunk missing out of the middle, and we're going to use these cylinders to evaluate the area. So what this is really going to look like is, and I want to draw in some rectangles to really represent the area, and I know I'm kind of got some of these kind of mixed up, or the function value mixed up there, but it's fine. So if I want to know what this would look like, and sorry, that's going to kind of look a bit bad, we're going to just take a ton of little cylinders with like divots cut out in the center, and we're going to use these cylinders with holes in the center to evaluate the area. Kind of think of it like a Russian nesting doll. You're going to be putting a cylinder and a cylinder and a cylinder, and as these cylinders with like holes in the middle, as their width gets infinitesimally small, we'll be able to find an exact approximation for the volume. So, and as I said here, this is going to look like this formula here, where r is equal to r1 plus r2 divided by 2. In other words, it's the average distance. And you can see that this is going off of this example up here. The change in r is r2 minus r1. And then height is just the height of this cylinder, really. So, and whenever we take a limit as this goes to infinity, we actually get the definite integral of from a to b of 2 pi x f of x dx. And it's important to note that 0, or a needs to be greater than 0, and b has to be greater than a. Alright, now that we've got this down, or this formula down, let's use it. So suppose I want to know the volume of the following graphs if I were to revolve it around the y-axis. Well, for this graph of the square root of x, this graph's going to look something like this. And of course, and this is after the rotation. Okay, So now what we're going to do is we want to, well, we know that we're going to be integrating from 4. And because we're evaluating at this value of 0 down here, or we want the curve to be encased by this value 0, we also have to make sure x value is also 0. So this is going to look like the integral from 0 to 4 of 2 pi times by x times by the square root of x. And we're integrating, in this case, with respect to x. All right. Now what we have to do is we're going to kind of simplify this. This is the same thing as x to the power of 3/2 if you add the exponents together. So we're going to get the integral from 0 to 4 of 2 pi times by x to the power of 3/2 dx. Well, this is now just a power rule integral. So we get 2 pi times by 2/5 x to the power of 5/2. And then plus c, but we don't have to worry about the plus c since this is a definite integral, and we're integrating from 0 to 4. Well, now what we're going to do is we're just going to have to evaluate this. Alrighty, so evaluating this at 4, I'm going to do the square root of 4 first, that's 2. So then we get 2 to the power of 5, which is going to be 2, 4, 8, 16, 32. 32 times by 2 is 64. Times that by 2 is 128. So we get 128 fifths times by pi minus it evaluated at 0, which is 0. So we get an answer of 128 divided by 5 times by pi for the volume. Alright, so now we want to find find the volume for the shape by revolving 1 over x around the y-axis. And we once again are being bound by 0, x is equal to 1, and x is equal to 4. So what this is going to look like is we have our logarithm curve here. Or actually, no, sorry, this is 1 over x. So it's going to look something on the lines of this. And we're rotating the shape around the y-axis. So this is going to look like the integral from 1 to 4 of 2 pi times by x times by 1 over x dx. Well, this 1 over x and the x will cancel, so this is really just going to be the integral from 4 to 1 of 2 pi dx, which is going to be 2 pi x, evaluated at 4 and 1. 4 is going to be 8 pi minus 2 pi, so we get an answer of 6 pi for revolving this around the y-axis using the disk method. Or sorry, not the disk method, the shell method. So now we just want to revolve the following curves around the x-axis. So this is kind of where I like to start thinking a bit more. I'm going to sketch out this curve. So we have this curve y is equal to the square root of x. And we want to know, and it's going to be bounded by this, and we want this area right up here actually. Kind of strange. But from y is equal to 2 and x is equal to 0. Well, let's see, how do I want... So really this area here, or I suppose what we can call the radius, r, is going to be 2 minus the square root of x. However, because we're not revolving around the x-axis, we want to know what these y values are. So we really want to get this into terms. Ooh, this curve might actually be a bit easier to do with the washer method. Give me a moment. Or not washer, but... Okay, now that I've thought about this a little bit, I think what I want to do is I'm going to get this function into terms of y, and then integrate it from the point 0 to 2, and then this should allow me to get this area and rotate it around. So, we are going to see that this is going to be y is equal to the square root of x. So we now have to solve this for x. So we get y squared is actually going to be equal to x. Okay. So now we're going to say that this is going to be the integral of 2 pi from 0 to 2 of y times by the function f of y, which is going to be y squared in this case, dy. Well, we have to now just simplify this using algebra, so we get 2 pi y cubed dy. Integrating this, we will get pi divided by 2 times by y to the 4th evaluated from 2 to 0. 2 to the power of 4th is 16, divided by 2 is 8. So we are going to get 8 pi for our answer, I believe. Alright, for the next curve now, I think I want to draw out a sketch for this curve. So, this curve, and because I need to find the vertex really, so actually what I'm going to do rather than sketching it out is I am going to complete the square. So we are going to get x is equal to, we're going to pull out a negative 3 y from the y squared, so this will become minus 4y. So then dividing by 2 and then squaring it, we will get 4 minus 9. But now we have to, because we're adding this 4, but we're really subtracting 12, we have to add 12. So we really get x is equal to negative 3 y squared minus 4y plus 4 plus 3. So we get x is equal to negative 3 y minus 2 squared plus 3. And this tells us where our vertex is of our parabola. So in this case, it is going to be 2y down, or sorry, 2y up, rather. And then it's going to have a value of 3. And this is going to be a parabola that opens to the left. And we really want to know what is this volume if I were to rotate this area around the x-axis. So this is definitely one where you would want to use the cylindrical shells, because we have this change in x, but whenever we go to, or really because we want to do the change in y, but I digress. But what I'm trying to say here is, because we have these two different values, we want to use the cylindrical shell method for one value of x. So, what this curve is actually going to look like is the integral from negative 1, or not negative 1, but 1 to 3 of our original function, which is negative 3 y squared plus 12y minus 9 dy. And we're multiplying this, by 2 pi times by y. And we're integrating with respect to y. So now I'm just going to pull this 2y out till the very end, or the 2 pi out, sorry. And we're integrating from 1 to 3. Distributing the y, we will get negative 3y cubed plus 12y squared plus, minus 9y dy. So we get 2 pi times by negative 3/4 y cubed plus 6y cubed. Sorry, this one should be to the 4th. Minus 9/2 y squared, evaluated from 3 to 1. Alright, this one's going to be a small bit of a mess to evaluate, but we can always use our calculators, so give me one moment. I realized that I did do something wrong. This should be 4, not 6. And if I did all of my math right, we should get 60 for the answer. Alrighty, well, that's all I have for you today's video. This one was a kind of bit shorter, and in general, I think this topic is kind of redundant. But I hope you all have enjoyed, and I hope you all have found this video informative. And if you did, please make sure to leave a like and subscribe.